I picked out a homework problem from chapter 2, sort of at random, to illustrate how I would solve that homework problem from start to finish, to try to give you a little idea if you're kind of struggling with where do I start, or what kind of things do I need to write down to get a good grade on my homework, or what kind of things would I need to do to solve a homework problem simply to prepare for a quiz or test. Um, any of those things would like to just work out a homework problem from chapter 2, start to finish, so that you can get an idea of how somebody else would solve that same problem that you've been assigned. So here we go. I've selected problem 223 to work out from start to finish. So let's go ahead and start having a look and start solving. So I'll read quickly the problem statement. That's the first step in problem solving, is pretty carefully reading what the problem says, the whole problem. It's a gas contained within a piston and cylinder assembly. It undergoes 3 processes in series. 1, 2, 3. Okay. Process 1 to 2, state 1 to state 2. Constant volume process from P1 equals 1 bar and V1 is 4 cubic meters to state 2, where P2 equals 2 bars. Okay. Next process, 2 to 3. Compression from state 2 to V3 equals 2 cubic meters. Compression. The pressure volume relationship it's given by a formula. PV equals constant. That's going to be critical for this problem. Now, finally, process 3 to 4, we start at state 3, end at state 4, and it's going to be a constant pressure process where the final volume is 1 cubic meter. Okay, and what's the assignment? It says sketch the processes on a PV diagram. You should be getting very familiar with how to do that, and also numerically evaluate the work done for each process in kilojoules. And so I picked this not exactly at random, because this is a classic candidate problem for a quiz or test. So this level of complexity of this problem would be very representative of a quiz or test question. Oh, and a quick commercial then before we get started. I'd like to recommend that you check out my recipe for problem solving. If you go to Jay's Toolbox YouTube channel, if you click on the playlist Homework Solutions, HW Solutions, you're going to see I've got a couple of videos that I recommend you browse. If not, watch completely. Problem Solving 01 and Problem Solving 02. That is a recipe that I adopted that my professors showed me how to do. I didn't come up with this on my own. My professors guided me, sometimes due to giving me low scores on my homework solutions, because I wasn't exactly following their recommended recipe, but I got better and better at it. I continued this problem-solving recipe into graduate school, and then once I got out of graduate school, I continued this practice on into my engineering career. So this is something you can train yourselves to do, and you can carry this skill on into your practice of engineering. So it's not something you'll just do just to solve homework problems, just to do well on quizzes and tests. It's a skill that you can have for the rest of your career. Okay, let's look for key words in our problem that we're going to solve. A gas contained in a piston and cylinder. That's a key. Gas and piston and cylinder, says we've got a closed system. The mass inside the piston and cylinder, the gas, is a fixed mass. That's going to be key for us. Also says 3 processes. It says the state of the gas is changing, starts at state 1, continues on to state 2, then to state 3, and then finally to state 4. So this is going to be a classic problem where you're not going to find a formula in the book that leads you to a single answer. This is going to be a key part of thermo. And so let's see, numerically, what are you asked to do in addition to drawing PV diagram that you do anyway? Determine the work out numerically for each process, 1 to 2, 2 to 3, 3 to 4. And you say, man, I can get to town on this. But let's step through and sort of follow a traditional problem-solving recipe. Okay, let's see. The 3 proposed processes and some key words. The process paths are fully defined in the problem statement. Process 1 to 2, it says a constant volume process. What's that going to look like on a pressure volume diagram? Process 2 to 3 gives the process path. It says PV, P times V equals a constant number. PV equals constant. What's that going to look like on a PV diagram? Process 3 to 4, a constant pressure process. What's that going to look like on a pressure volume diagram? So the key here is to recognize that the process paths, the description of pressure versus volume is given for each of the 3 processes. That's going to be the method by which you're going to solve this problem. Oh, another key word in process 2 to 3, it says compression process. So I picked the compression process. What does that mean in common sense? Applying your own common sense, what would a compression process be? Would it make sense that a compression process, the volume of the gas would shrink, be made smaller? You're compressing the gas. How about pressure? What would your common sense tell you about a compression process? Let's say you have you've got to pump up the pressure in your bicycle tires. That's a compression process, isn't it? So you'd expect the pressure to go up, volume could go down. These key words can help you solve the problem. All right, let's get started drawing the pressure volume diagram. Let's start with state 1. And this is just a screenshot from my own personal solution from 2022. I drew my axis, pressure on the Y, volume on the X. I'm starting at state 1, so I'm just going to put a dot really just about anywhere on my diagram. It says constant volume. What is a constant volume process going to look like on a PV diagram? It's going to be a vertical line. V equals constant. So I labeled my state 1 here. I didn't label it 1 bar. I labeled it 100 kPa because I've done enough of these problems to know that I've got to be very careful with units, and it's going to be very handy to deal always in kPa and not in the unit bars. So I labeled state 1, 100 kPa, 4 cubic meters. All right, constant volume process, and it says P2 is 2 bars or 200 kPa. Obviously, vertical line headed upwards, increasing in pressure. All right, so there's the start of my PV diagram. Next process, it says, in the problem statement, it said PV equals constant. That's the process path, okay? Compression process. So at least I know the volume's going down from state 2 and the pressure's going up. At least I got that part. So I know I'm sort of headed up somewhere up and to the left. What's PV equals constant? Well, at least you know that P2V2 is some number. If P2 is given, and let's see, V1 equals V2 equals V1. So P2 and V2 are both given. So do you see that you could immediately calculate the constant value by multiplying P2 times V2? You get a number, all right? What does the path look like? Well, let's rearrange PV equals constant. Let's solve for P only. P equals constant divided by V. What does that look like? Think back to high school. I hope in high school you became good at plotting Y equals A divided by X. Y equals A, where A is some number. A over X. What's the shape of Y equals A over X from high school? It's a hyperbola. Now, that is something that I would expect you to know. Not something you got to memorize. You should know that. Y equals A over X. Well, back to thermo, P, that's kind of like Y. V, that's kind of like X. So P equals constant over V is a hyperbola. P equals constant divided by V. So now you can draw your sketch. I've drawn, it's not the most beautiful hyperbola in the world, but at least I've curved it like a hyperbola should be. And we're going from 2 to 3 up and to the left. So it's a curve, a hyperbolic curve. You must draw that down. It is not a straight line. You must draw that down. Hyperbola. And I've shown in my solution, I called it a hyperbola. PV equals constant. Okay, easy part, 3 to 4. It says constant pressure process. Well, on a PV diagram, that's going to be a horizontal line, isn't it? P equals constant. And also given in the problem, the volume decreases. It tells you that V4 equals 1 cubic meter. So that's what tells you that you're going at constant pressure to the left, horizontal line to the left. We finished our PV diagram, and hopefully you might get at least half credit if you quit there. But let's continue on with the numerics. Okay, there's a value to knowing that the process path is defined. So go back to your textbook reading and chapter 2. When you have a closed system, and a quasi-equilibrium process, in other words, quasi-equilibrium process is one in which the pressure volume path is fully defined mathematically. And in this case, it is mathematically defined. V equals constant, PV equals constant, pressure equals constant. So all of those are fully defined paths. Once you have, for each of those, you go to your textbook and say, we have derived that the work out for a closed system, quasi-equilibrium process is the integral from state 1 to state 2, or any states, okay? Integral of PdV, okay? So that's something that you really, really need to understand. Chapter 2, derive that for closed system, process path defined work is the integral of PdV. And so now that you have your PV diagram, it's easy to execute this integral of PdV for each process, and you've got your numbers. But that's your, I hate to use the word formula because it's more than a formula. It is a fundamental statement of the work done for a closed system undergoing quasi-equilibrium process. All right, so let's see what we've got. How about process? Let's go all the way from 1 to 4. Integral of PdV. This should be back from high school as well, from high school. Integral, and integral. What's the physical meaning of an integral? It's the area under a curve, the area under the process path. Area under the curve is the visualization of an integral. So how about the integral from 1 to 4? Will it be a positive number or a negative number? The area under the curve, I've crosshatched it in my solution, but it's going to be a negative number because you're integrating from right to left. Right to left, the numerical integral of that is a negative number. Left to right, the integral area under the curve, positive. For this problem, we're going from right to left. We expect the work out for the whole process, 1 to 4, be a negative number. All right, let's move on because we're assigned to do each work individually. The work from 1 to 2. See, I've called it W1 to 2. Why am I saying that's 0? Why is that 0? Ah, easy. Because with my eyes, I can see that there's no area under the curve from 1 to 2. So the area under the curve is 0. Mathematically, dV is 0. No change in, not even an incremental change in volume. So the work from 1 to 2 is 0. I'm going to write that down in my solution because that's part of what's been requested. There's partial credit. 2 to 3. The area under the curve from 2 to 3, it's going to be a negative number. And a little bit more about that in a minute. But you see that I've got to go right back to the integral of PdV. And what I'm going to have to do is get pressure P as a function of V. That's the only way I can perform the integral, is to get P as a function of V. And of course, you see it's going to be a negative number, but we're going to dissect that a little more in another slide, okay? So for right now, you know, the work from 2 to 3 is going to be negative number, and we're going to do the math a little bit later. Okay, let's see. 3 to 4, constant pressure process. We're going to go right back to, we're going to write it down on our solution. The work from 3 to 4 is the integral from 3 to 4 of PdV. Wow, this one's really easy. This is an easy integral, isn't it? Because P is constant. I will pull that out of the integral. The integral of dV is just V. Evaluated from 3 to 4, so it's simply going to be, well, that constant P3 times V4 minus V3. Okay, you see that this is not a formula. This is the result of a mathematical expression that you're evaluating, not a formula. Okay, now looking ahead, we're going to have to find what P3 is. It's going to be very easy. We'll do that in our solution. Okay, the key to your success basically in this class, be able to integrate a simple process path quickly, keep your units straight. We're going to go through that and understand what you're driving for. Work out needs to be in kilojoules. Okay. And so what I'm going to talk about in a little detail is when units of pressure are given in bar, you're going to discover that it's very convenient for you to immediately change pressure in bars to pressure in kPa. Your volume is going to be in cubic meters. Okay. So here we go on the numerics of this. Another commercial, I encourage you to watch my video, Working with Units in ME2134. So working with units, you'll be able to find that on my YouTube channel, I think under Fundamentals. All right, so now we're going to do the numerical solution. So we're going to start with process 1 to 2. We're going to write down the given information. And so notice here, so I wrote down all the stuff that was given to me. I just wrote it down. And in my world, I write it down in Excel and I turn the cells yellow. That's the key to me that I'm fat fingering in a number. V1 is V2, that's 4 cubic meters. V3 is 2 cubic meters given. V4, I've got a typo here, don't I? V4, not V41. V4 is 1 cubic meter. P1, notice here, I didn't even write down bars. I just wrote P1 is 100 kPa. I do that in my head. Okay. P2, given 200 kPa. And then another thing in my solution, then I'm going to write down the work from 1 to 2 is 0. I'm going to clearly show that in my solution because that's going to be good, easy partial credit. Now, 2 to 3, the hardest part of this problem. Here's our sketch. We go back and look at our sketch, and I've got my governing equation, closed system, quasi-equilibrium process. The work from 2 to 3 is P dV. P is equal to constant divided by V. So in my, do you see that because of the given information, P2 and, well, V2 equals V1. P2 and V1 are given. Because of my sketch, I see that V1 equals V2. So look, I can bang out a number for the constant immediately. In my world, as a student and then as a practicing engineer, I went ahead and solved for that constant immediately. And so here's what I do in my solution. The constant is P2 times V2. It was all given. And so I've got 800 is my constant value. I did a units check. So do you see P2 times V2? I've got kPa times cubic meters. How does that work out in terms of units? Well, I've got to remember what a Pascal is. A Pascal is a Newton per square meter. See that? I've got a K over there. So I've got this K trailing along, cubic meters. And now I can visually see, okay, I've got cubic meters in the denominator, meters squared in the numerator. I'm sorry, meters cubed in the numerator, meters squared in the denominator. They're going to cancel. So I've got units for my constant of kilonewton meters. Well, what's that? What's a Newton meter? That's a joule. So sure enough, the units of my constant are kilojoules. Now that's going to be handy. That's working out for me because let's go back and look at the math. Constant, I pull it out of the integral, pull a constant out of the integral. I've got to integrate dV divided by V, or V to the minus 1 dV. I remember this from high school, and you're going to need this in this class. The integral of dV over V is the natural log of V, natural log of V. Okay, so I've got the natural log of V3 minus the natural log of V2. Oh, I didn't write that down, did I? That's because I've done this so many times. I remember that the natural log of V3 minus the natural log of V2 is simply the natural log of V3 over V2. I learned that in high school. And so that's how come I quickly, in my solution, work from 2 to 3, I do the integral is constant, P2 V2 times natural log V3 over V2. This is not a formula from the book. This is something you work through and you derive back from the fundamentals. Okay, so now back to numbers. The work from 2 to 3, integral PDV, just like in my handwriting, it's the constant times natural log V3 over V2. Numerically, I've got negative 554.5 kilojoules because I've got my, what's the units of the natural log of V3 over V2? Dimensionless. V3 over V2, dimensionless. The natural log of a number, dimensionless. So my units are kilojoules, same as constant. Negative 554.5 for process 2 to 3. Hardest part of the problem. Okay, the last one, constant pressure, 2 to 3. We're given that V3 is 2 cubic meters. We're given that V4 is 1 cubic meter. So let's see, the integral of PDV. So let's see, shame on me for not writing this out on the slide. Integral PDV for process 3 to 4 is constant pressure, P times V4 minus V3. I need pressure. I need P3, which equals P4. So I think back, I look at my given information, and I see from my process path 2 to 3, I see that P2V2 equals P3V3. And I study on my given information. P2 is known, V2 is known, okay? V3 is known, given. So I can solve for P3, okay? And it's simply P2V2 over V3. One equation and one unknown. So P3 is 400 kPa. Okay, that's you've got to get that on your own. You're not given it. Now you can go in and apply your work equals integral PDV, constant pressure. So P3 times V4 minus V3. Bang that out, and you've got negative 400 kilojoules. And just for completeness and in illustrating worked out problem, how about PD? Let's do a unit check on P times delta V. P, kPa. V, delta V, cubic meters. Well, let's write out what's a kPa. It's a kilo, Newton per square meter, times cubic meters. Okay, got some cancellation here, kilonewton meters. Sure enough, P delta V, that's got units of kilojoules. So let's summarize the work. Let's summarize the work. Again, if I'm going to turn this in for credit, I want to be sure that the person looking at my solution gives me all the partial credit he or she can possibly give me. The work from 1 to 2, 0. The work from 2 to 3, negative 554.5. I'm making it clear. These are my results. Work from 3 to 4, negative 400 kilojoules. I'm stating units in addition to numbers. And then I add them all together to get the work from 1 to 4, negative 954.5. So sort of finally, when I'm solving problems, both as a student, graduate student, and as a practicing engineer, instead of just circling a number with a unit, I write out a sentence. Work is done on the closed system in the amount of 954 kilojoules. So that's a nice way to say the result. Work is done on the system, since it was negative, in the amount of 954 kilojoules. Okay. Do want to point out, look how in my work, I'm always stating units in addition to numbers throughout my work. Another thing you might have picked up on in this solution is that the key to success in this class is not simply thinking that you're going to be applying formulas that are given to you or that you're fishing out of the book. Some sections will be allowed to use formula sheets. I don't recommend that, but that's okay. If you're allowed to use a formula sheet, you should. But look, this is your best formula sheet. So I really want to recommend that you think about what are my fundamentals that I can get into my head, that I can really learn and not worry so much about formulas, formulas, formulas. So your head and the fundamentals that you're getting into your head, that's your best formula sheet. So that's my advice for you for today as you're working through homework, getting better at performing on quizzes and tests. Okay, so what's the summary of this worked out problem from chapter 2? Start with a sketch. Always start with some kind of sketch. Plan your work. Don't just start putting numbers down on paper. Start with the fundamentals. On this problem, we used work equals the integral of PDV for a closed system undergoing quasi-equilibrium process. That was our fundamental that we used. Okay. Blindly using formulas is a losing proposition for this class. The sooner you can get over that hump, the better you're going to do in the class. Check your units as you go along. Units can be your friend, and it's necessary that you work with units throughout your solution. And certainly in the final result, you must include units with the numerical results that you've achieved. So express results, make them clear in your solution, including the units. Okay, I had a little mental lapse there on how to quit sharing. I finally remembered how to quit sharing. So I hope that's helped you. So it's my intention to pick off some one or so problems from each chapter and illustrate from start to finish how I would solve that problem. Of course, normally I try to provide homework solution tips for all the homeworks that you're assigned in this class, but I don't show solutions for much of anything. So I hope that helps. And good luck with your homework solutions, and good luck as you prepare for quizzes and tests.